This is a document that's downloadable at the bottom of the class web page that sort of summarizes the main results in sections 4 and 5 of chapter 3. Section 4 is about bases, 5 is about dimension. And all of this is a lot easier to understand if you think of a geometric example of a subspace, say a two-dimensional subspace of R3, like the xy plane, where all vectors in that subspace W have a third component of 0. Okay, to start with two definitions that we saw earlier, a spanning set is a set of vectors such that a spanning set for a subspace W is a set of vectors such that any vector in the space can be written as a linear combination of those vectors. And for example, any two non-parallel vectors in W, if W is the xy plane, that is the set of all vectors whose third component is 0, that's a two-dimensional subspace of R3. Any vector in that space can be written as a linear combination, for example, of I and j, where I is the usual vector 1, 0, 0, j is 0, 1, 0. Any vector x, y, 0 can be written as x times I plus y times j. So I, comma j are two vectors that form a spanning set for that two-dimensional subspace. Now, you can have a lot of other spanning sets, basically any two vectors that are not parallel. You can write any vector in the xy plane as a linear combination of those two. You can throw in a third vector. So for example, you could have a set of three vectors, I, j, and your third vector would be 1, 1, 0, say. Then still any vector in the xy plane can be written as a linear combination of those three. In fact, they can be written in many ways. They could be written as a vector xy0 in W can be written as x times I plus y times j plus 0 times that third vector, but could also be written as a linear combination of j and the third vector with a 0 coefficient of I and so forth. So there's a lot of ways to write any vector in W as a linear combination of those three vectors, I, j, and 1, 1, 0. So basically you've got more vectors than you need. That's the spanning set that's kind of redundant. Any two of those vectors would be sufficient, but three is still a spanning set. Okay, linear independence, that we defined way back in chapter 1. A set of vectors is linearly independent if the only linear combination equal to 0 vector is the trivial one where all the coefficients are 0. And a little more intuitive definition of linear dependence is that means that at least one vector in the set can be written as a linear combination of the others. That would be linearly dependent. For example, the set of three vectors I just gave a minute ago, I, j, and 1, 1, 0, that is the vectors 1, 0, 0, 0, 1, 0, and 1, 1, 0. Those are not independent because the third vector can be written as I plus j, so it's the kind of redundant spanning set. But anyway, this is a definition of independence that we got back in chapter 1. Okay, so those are old definitions. You should be familiar with those. Now in section 4, we define a basis as a linearly independent spanning set. So basically it's a spanning set that doesn't have any redundancy in it. If your spanning set is dependent, that means that anything you could span with those vectors could be spanned without one of them. If one of them is a linear combination of the others, then you can get rid of it and still span the space. So a basis is a linearly independent spanning set. And then there's a theorem that says if you have a basis for a subspace, then any vector in W can be written in one and only one way as a linear combination of those vectors. And the proof is pretty simple. If a basis means it's a spanning set and independent, the fact that it's a spanning set means any vector in the subspace can be written in at least one way as a linear combination of those vectors. But if they're independent, that is, if it's a basis, then there's only one way. And to prove that, you say, well, assume there's another way to write them, the vector w. Let's say there's one linear combination of those p vectors, and here's another linear combination, another way to write w, typical element of the subspace. Suppose there are two different ways of writing them as a linear combination of w1 through wp. If you subtract the two, you get a1 minus b1, w1, etc. equal to 0. And the fact that the vectors are independent means that you have a linear combination equals 0. The coefficients must all be 0. Therefore, a1 minus b1 must be 0. So a1 is the same as b1 and so forth. So back to our example, which helps you understand intuitively what's going on. The three vectors I, j, and 1, 1, 0 are a spanning set, but they're not independent, so there are many ways of writing any vector in the xy plane as a linear combination of those three. If you throw out one of them, say throw out the third one, then I, j is a basis for the xy plane, and there's one and only one way of writing any vector as a linear combination of those two vectors, because it's a spanning set and it's independent. So that's basically the main point of having a basis, is that there's one and only one way of writing anything in the set, in the space, as a linear combination. There are many bases. Like I said, those three vectors that I mentioned above, 1, 0, 0, 0, 1, 0, and 1, 1, 0, you could actually take any two of those and that would be a basis. All three together is a spanning set, but it's not independent, so it's not a basis. So that example, I think, helps you understand what's going on in general. We'll be talking about 10-dimensional subspaces of R20, and we're going to see that any basis of a 10-dimensional subset, a subspace of R20, is going to have exactly 10 vectors in it. So here's the theorem that says what I just stated, that all bases for a given subspace have the same number of vectors, so we can call this number the dimension of W. The proof is a little bit complicated. I'm not going to go through it here. You're not responsible for it. If you want to see it, you can download this document from the bottom of the class webpage, but it's intuitively reasonable. Like I just said, if you have a subspace, have a subspace of R20, that is the set of all vectors with 20 components. If you have a 10-dimensional subspace, then there are a lot of different bases for it, but they all will have exactly 10 vectors in it. If they have more than 10, they can't be independent. If they have less than 10, they can't span the space. Okay, here's another theorem that we're not going to prove. Well, the proof is on this document, but it says that any set of p independent vectors is the basis for a subspace of dimension p. So my example of a 10-dimensional subspace of R20, for example, one example of a 10-dimensional subspace of R20 would be the set of all vectors whose last 10 components are 0, so 10 components are non-zero. Then there are a lot of different bases for that 10-dimensional subspace, but they all have exactly 10 vectors in them, and this theorem says that if you have 10 vectors, if they're independent, they're guaranteed to be a basis. They're guaranteed to span it. A basis is an independent spanning set. So if you have any set of, if the dimension is p of a subspace, 10 in the example I just gave, 2 in the example of the xy plane, then any set of 10 vectors, independent vectors, is the basis for that subspace. The xy plane is dimension 2, so any 2 independent vectors would be a basis. And the fact that they're independent, well, a basis has to be independent and a spanning set, and we're assuming they're independent, so basically you need to prove that if they're independent, they're guaranteed to span the set. So if you have 10 independent vectors in a 10-dimensional space, you can be sure they're going to span it, and the proof is below. Any 2 independent vectors in a two-dimensional subspace like the xy plane are sure to span the space. Any two independent vectors in the xy plane, any vector in the xy plane can be written as a linear combination of those two. The proof is a little complicated. We'll skip it, but it makes sense geometrically and when you think about R2. And so let's say you have a subspace of dimension p. In our example of the xy plane, p would be 2. Then if you have any set of less than p vectors, it can't span the space. If you have more than p vectors, they can't be independent. And so if they're less than p vectors, they can't be a basis because they can't span the space. If they're more than p vectors, they can't be a basis because they can't be independent. In our example of the xy plane where p is 2, if you only have one vector, can't span the space, therefore not a basis. If you have 3 or more vectors, they can't be independent. You can't have 3 independent vectors in a two-dimensional space, therefore also can't be a basis. So any basis has to have exactly 2 vectors in a two-dimensional space. However, that doesn't mean that any 2 vectors in a two-dimensional space are a basis. They have to be independent, and if they are, then they span the space.